And so Geoff will talk about his GDV, so his verification, so his attempt to do verification with LambdaPi on Vampire in a slightly different way. So we had the talk by Anya, where she talked about changing Vampire to do proofs. And what Geoff is trying to do is something different, namely not changing the solvers. Geoff, the floor is yours.
Thank you. Yeah, so the core of this talk came out of the work I was doing at ENS Paris-Saclay, integrating LambdaPi into the bottom end of my verifier GDV. But since then, I've done more, and I've been sort of philosophizing a bit on why do I do this? Why am I spending my summers in France? Well, there's good reasons, but why do we want to trust and when do we want to trust? So I'm going to sort of hammer some stuff on the front about that. And then at the end, I want to talk briefly about some of the experiences we had at the competition this year and some of the proofs that came out and some of their features that are interesting and worth discussing. So it's a matter of trust. And what I'm trying to go is, what are we trying to trust? And so when we run a theorem prover or any software, two things come to my mind. Firstly, is it giving the right answer? You know, does it say theorem or non-theorem correctly? That being the status of the problem. And then secondly, do we want the artifact to be correct? The proof, the model structure, whatever it is. There's two things going on there. And then I thought to myself, well, why exactly should I do this? And so I found two reasons in my head. One is you're trying to show that a tool or a tool chain works reliably and will reliably give you the correct status or the correct artifact. An example of that is work I did at NASA. We had a tool chain to do some verification of software and a certification system. And we wanted, the FAA, in fact, wanted to know that this tool chain was reliable. So they didn't actually care about the individual proofs. They just wanted to know that the tool chain was correct. And then in other situations, what people always say, the mission critical proofs, is that we really want to know, is the proof a correct one? And I'd always give this example, the well-known Aunt Agatha problem. If you give it to ChatGPT or Gemini, it quite often blames the butler, where in fact it was a suicide. And if you're in Texas, the butler's only got 2 weeks before he's sitting in a chair with electric cables connected. So you want the actual proof artifact to be correct in those situations. And in general there, you've got untrustworthy tools, sub-symbolic systems, and you want to then verify them using a symbolic system to check that these sub-symbolic statistical systems are correct. So that sort of gave me, you know, when, what, and where. And then I thought, well, what's the whole process? What do I go through when I'm looking at provers in the TP-TP context? And so I thought, well, firstly, when should we be doing this, building this trust, doing the checking of the status and the proof artifact or a model artifact? Well, clearly developers do it during development to, you know, test what they're doing and making sure they're doing it right. And then there's users who want to, for particular, their artifacts, you know, they get a proof and this proof matters. It tells you who's guilty or some medical conclusion. They want to build trust in that. And there's sort of situations, like medical ones, you might have a pacemaker that runs on software. The question is, should you deploy it in somebody's chest before you've built trust in that software, or should you wait, but then the patient dies because you waited? So there's a notion of when it's worth waiting. And so then I was at Dachstuhl in January or February, and we were talking about sort of how do you do this verification? And many people there had this idea, well, there's a theoretical story and we have a trustworthy core inside Isabel. And Haniel Barbosa said, well, I trust the Isabel core. And my answer was, well, why do you trust it? And he said, well, it's 4,000 lines of ML. And I said, you trust 4,000 lines of ML written by a graduate student in Munich? I mean, is that sort of is that a way to trust software? And so I don't do that. And also, I think there's theoretical limits there. So from the real practical point of view, in which that's the sort of world I live in, is I think of things going like this little flow chart. For any system, maybe a theorem prover, whatever your system is, you give it some problem and you've got a choice. Is this a trusted system? And if it's not, well, then you've got an untrusted solution. So the next step I do in theorem proving, I run a new theorem prover across the TP-TP. I see, do any of its results contradict what I know? Does it meet expectations? So I'm just looking at the status there, not at the proof artifact in my case. And if it contradicts, 3 other theorem provers, I write to them and say, hey, there's a bug. And I think I don't trust you a little bit. I accumulate negative evidence. And this seems to be the way I think some of the competitions work. The answer is the majority is correct. So that's democracy. On the other hand, if the status is correct, I then want to check the artifact, the proof artifact, or the model. And first thing, is it syntactically well formed? And strangely, in the competition, I got lots of badly formed proofs. But if it's well formed, you can hand it to the verifier. And that's where my GDV kicks in. And whatever verifier you love to use, Calcutta or some SAT verifier. And if it doesn't pass the verifier, that's negative evidence. If it does, whoopee, you've got positive evidence. And then one of the things I noticed, given a verified solution, is it usable? Can the user comprehend it? And I was just talking to Matthias now. I have theorem provers with genuine old-fashioned inference rules, which have 600 parents in the inference. Well, is that usable? I mean, 600 parents, what do you do with that sort of inference? Can you understand it, make use of it in a practical sense? So I'd say if it's not really comprehensible, in the trash, otherwise it's useful. Of course, this upper circle goes round, you accumulate evidence to the point that you trust it. So for example, I've always said, I trust Otter, the old Otter prover by Bill McCune, because it's battle hardened. So many people have used it in different contexts. I trust it based on its usage. And when you have trusted solutions, you can kind of short circuit all of that. So that's kind of the process that I run in my world. And I think we genuinely all do that. You write a bit of software, you don't trust it because you've been hacking it. And you say, wow, does it give the right answer in all my test cases? And if it gives a wrong answer, you immediately go back to your source code. But if it gives the right answer, you might later verify the artifact that comes out with some verifier that you trust. And so, taking that directly into the theorem proving context, well, I think I can skip some of this. People know what automated theorem proving is. I hope everybody knows what the TP-TP world is. If you don't, please take out your laptops now and make that your home page. So every morning when you open up your laptop, you're in the right place to do something sensible. Of course, it's my large collection of problems, solutions, a language, this beautiful language I have, the great big beautiful language. Thanks, Donald Trump. And the ontologies for what the results can be out of a theorem prover, positive and negative ones. A whole lot of online services, which I'm sure many of you have played with in some way, for preparing problems to be put to tools, for running tools, and for analyzing the solutions. And it's my verifier that sits in this last block over here. And then, of course, there's a bunch of other things. And I've just put in for the TP-TP Tea Party number 15 at Flock next year. You should all attend. This is something I'm going to mention. We all know the CADE competition where we compete, the provers compete. Next year, we're going to have a parallel competition called Prover, being run by Julie Kalia and Simon Gouliard, where we're going to have verifiers competing. And so if you own a proof verifier that can read my format for proofs, please enter our Prover competition. We're going to see if we can fool your verifier or how well your verifier can perform up against proofs and things that are known to be bad proofs. All right, so that's that story. We know that in software, of course, bugs are reality. I show this slide because I just love this picture. Theorem provers look like this to me. They're a spaghetti of code with bugs in them. It's just, and some vegetables, it seems. So, of course, there's various ways that theorem proving software can be wrong. It can be incomplete. Well, we accept incompleteness because we have finite resources, but unsoundness, giving the wrong answer. And occasionally I've found this is that they give the correct status, but the proof artifact is wrong. So they give the right answer for the wrong reason. And that's kind of a sad thing too. So we want to deal with that. And I mentioned the empirical process. So now I just artifact, it's an ATP system over here, whether it's trusted, what comes out are proofs, right? Does it meet the expectations against what other provers have said or what I know for some theoretical or external reason? And then I run a logical verifier. And in my case, again, it's the GDV, and we have verified proofs. Again, this cycle goes round, and everybody has in your heart. If I say to you, vampire, I say, do you trust vampire? And if I had a big picture of you all, I could say, raise your hands. And do you trust vampire to always give you the correct answer? Sort of, mostly, but not always when it's a new release, because I find mistakes when I do my testing and I report it to Martin and Michael, and they say, oh, shit, damn it, we made a mistake, let's fix that. But if you ask, do you trust the e-prover from Stefan Schultz, you might have a different degree of trust because it's engineered in a very sort of solid way. And if you ask about other provers, you might say no. So this level of trust here comes through an accumulation of evidence of your own, and possibly if you look at my database, you say, yeah, man, vampire always gets it right. Fantastic, and you trust it. Or you might say, that particular prover keeps making mistakes. I don't trust it. And so that's what's going on. So then we have to think, well, how do I represent proofs? For those of you who don't know about the proof format, don't you love my pictures of trust? This is from the South Korean army. That's what you have to do. You have to sit and another guy shoots an apple off your head. I wanted to get a picture of who was it? The guy Robin Hood or whatever, but I thought that one was more, this one, if you make a mistake, it's really going to hurt.
It was actually William Tell, not Robin Hood.
William Tell, thank you very much. Yeah, so this is William Tell. Actually, it's with a Korean accent, but anyway. So people might be aware of the TP language. Let's just look at some examples. It's Prolog-like. It's got a very nice human-readable syntax. It's not S expressions, which are better for computers, but worse for people, because people don't read bracket.
I now officially disagree.
I know, yes, but you'd be wrong. It's okay to disagree when you're wrong, Stefan. Anyway, so people might be familiar with this language, and here's a first-order example. It's very Prolog-like. The binary operators are infix, and it's got opportunity to annotate annotations in a flexible but fixed format. And an important part of this is that every formula is given a role to say to the tool you're giving it to, this is what this formula is in the context of what I'm sending you. So that would be an axiom. In contrast, if you look at the same language is used for problems as it is for proofs and for models. So here's an example, part of a proof that comes out of, it looks like Otter to me, or Prover 9. And this is a lemma. It said this is an important sub-step in the proof. And notice here that in a proof, the inference steps are recorded. There's like that, which is this. It says that's the name of the inference rule. And GDV doesn't care what you write there. You can put black magic, and that would be fine as well. What GDV relies on is this status over here that tells you what is this formula with respect to its parent. So this is saying this formula is a theorem with respect to its parents. That's a very common status, but it's not always the case. When you do scholemization, the scholemized formula is not a theorem of its parents. It's a satisfiability preserving step. When you negate the conjecture, when you're doing a proof by refutation, you get a counter theorem because you're negating it. It's not a theorem. And then you can put the parents. In this particular example, this unit deletion has got two parents. One is a nested inference, which hasn't been written out. So I don't know what that formula looks like. It's somewhere in there. And the other parent is formula number 11, which would be higher up in the file. So this syntax sort of works. And even if you don't think it's the best in the world, it is. And it's all online and hyperlinked, and we have it in the grammar for the language in Antler, so you can make a parser as fast as you want. It sits in a hierarchy of languages, people might be aware. TP-TP started off in CNF back in 1990s. Then we went up to first order form, and we actually jumped from there to higher order form. Then we filled in later with typed first order, which can be monomorphic or polymorphic. Extended type first order, that's with Boolean terms, monomorphic, polymorphic, and higher order monomorphic, polymorphic. And hanging off those are the non-classical logics for modal, deontic, and things like that, both in extended and higher order form. Most recently, and I need to update this picture, there's a talk on at Frocos next week or whenever it is in Reykjavik. We now have dependently typed higher order logic coming into the TP-TP world. It will be released somewhere in the next couple of months. There will be a new release of the TP-TP. But if you're interested, the paper's in Frocos. The work is largely that of Daniel Renalta and Cesare Kalashik. No, Cesare Kalashik. All right. So there's a proof format. Let's just do it by example. Here's a little story that all men are created equal. John is a human. John got an F grade. Someone is a human who got an A grade. An A grade is not the same as an F grade. Grades are not humans. Therefore, there is a human other than John. And I did it in first order logic. So we've got some axioms like this one. For all H1 and H2, if they are humans, they are created equal. Some other axioms that capture this. And the conjecture is there exists H that is a human and is not equal to John. This is the proof by E, it looks like. Stefan, are you still? I think I heard Stefan's voice.
I'm still here.
That looks like yours, doesn't it?
Also,
Yeah,
it's
RW, that's you. All right. So how does a proof look like? Well, the first thing is I print out all of the problem formulae, because it's really important to check that your proof is a proof of the problem that was sent in, not a proof of something else. And then we've got the steps here. Here we see the negation of the conjecture going on. And notice the status is counter theorem, which indicates that when you're verifying, that you should be checking that this is the negation of that correctly. And then there's some here we see the scholemization step. There's actually more details you have to provide these days. I need to update this slide. But notice here, this is a satisfiability preserving step. Stefan, I hacked your proof to make this happen. And so that's also not a theorem. And now we see some inferencing. Let's have a look here. So let's look at this, number 28. The inference is F equals A, and it comes from doing a RW, whatever that means. Thank you, which is a logic. I don't mind. You can, and it's a theorem. And the parents are this inference over here, which is number 17 and number 25. So 17 is the grade of the scolem is A. 25, John is the scolem. So you can conclude, I suspect that gives you the grade of John is A, that internal one. And then with number 14, the grade of John is F, so it tells you F equals A, which of course then leads to a contradiction. And so this is the sort of artifact that I verify. The key in that, just as I showed in that proof example, is the status of each inference, which tells you the semantic relationship between the parents of the inference and what's inferred down the bottom. And it's in this success ontology, this is the ice cream ontology. So if you get nothing out of this slide other than there's an ice cream ontology in the TP-TP, that's good for me. But in particular, what I do is look at the various ways an inference step could be successful. For example, the common one is, the common one is that the inferred formula is a theorem of the input formulae. Why am I not getting my tools here? Hold on. But in some cases, we saw that before, is for when you're negating the conjecture, And I also have status for verification that we'll come across later. So these status values, which are fully defined on a semantic basis, tell you the semantic relationship between the parents and the inferred formula. And that's all that you need to know in order to do the verification. You don't need to actually implement every inference rule to do inference rule replay. And the reason why I don't believe in that, and I don't believe that any verifier that believes in inference rule replay, I don't think they will ever succeed. The answer is this, is that every Tuesday morning, Andy Reynolds wakes up with a new inference rule in his head, and he implements it by Tuesday lunchtime. So any verifier for SMT coming out of CVC5 is always going to be playing catch up. When Stefan invents a new inference rule, he just says, it's an inference rule that does theorem. And I say, cool, I don't care what you did. I'm just going to check that you did take some input and produce a theorem of that input. So this was what my talk was supposed to be about. Here's how GDV works. I just got to change something in my tools here. All right. So what do? First thing I do is structural verification, as we see over here. This is making sure that it has the proof has the correct structure. Is it acyclic? If it's a refutation, does it end at false? When you negate the conjecture, you never do an inference between the negated conjecture and the conjecture, because then it's too easy to get a refutation. I look at things like assumptions. If I'm doing proofs that come out of the Mizar library, they make assumptions. Have you discharged all your assumptions? And it was in the competition this year that I implemented this checking, much of this checking, and that revealed weaknesses in the proofs that came out of pretty much all of the provers in the competition this year. And you would think getting the structure correct would be the easy part, but it turns out that people made mistakes there. Having done that, I then do semantic verification. Step number 1 is up at the top here. I make sure that the leaves of the proof across there do actually come from the original input problem. So you are demonstrating a proof of the original problem, not something else that you made up as you went along. Then I do look at the status, the semantic status of each inference step, and I'm outlining there. The most common one, of course, is theorem. It's a logical consequence. And for that, then I generate a proof obligation of the parent to the inferred formula I. So the inputs P1 to Pn, and then I give it to something I trust. And I used to give it to Otter, but I admit Otter's really not strong enough anymore. So I tend to use E over here because I trust E. Stefan, the $10 will be in the post. But of course, in other circumstances, you need to do something different. I mentioned counter theorem. When you negate the conjecture, there's something you have to do a different check. When you do scholemization or any other interference, you need to do something different. And of course, scholemization, everybody's all up in arms. You better use Hilbert epsilon terms, or you better do this. And Michael Rawson and I have got another way of using higher order logic based on Dale Miller's kind of ideas. But you need to do something different over there when you're doing scholemization and similar things. In fact, this is a topic of great debate between the vampire people and I. They do all sorts of weird inferences. Clearly, those guys do rock cocaine when they invent their inferences. It's weird stuff. So that's what happens. So, and you can run this online if you want to. So I've got, oops, sorry, I don't have that one up over there. E, what's the latest version of E, Stefan? 3.3.0. Yeah, like that. Yeah, there's the latest one. And there's his proof of the Aunt Agatha problem. And everybody, I guess, knows the Aunt Agatha problem. And so you can hand it over to, have to update that. And you can choose GDV, your favorite verifier, and push the go button. And it didn't find E's solution. I'm sorry, I have to update my slides. The way to do it would be then to go into the interface, and I want to use pos 001 plus 1 from E, and hopefully this works now. I should have checked. All right, and now that's been sent down to my server in Miami, and it's going through each of the inference steps that from E's proof, checking each one. And after a while, that will pop up with a proof. I can come back to it. But now, this is eventually the core of what this talk is. What if you don't trust Otto? What if you don't trust Stefan? What do you do? And so this was the work I did with the people at ENS Paris Sutcliffe. Rather than using Otter down here, we started using Xenon Modulo from Geoff. And what Xenon Modulo will do, as the same as what Anya spoke about earlier today, is output LambdaPi terms, and then we put those all together and use the LambdaPi checker or one of the other LambdaPi term checkers in order to verify the proof. All the structural verification still takes place. And at the moment, I've got this latest version of my scholarmization checker called Ask, written with the help of Alex Steen. And so people, for good reason, I guess, trust the Deducti framework and all the work that's been done there. If I look at a bunch of LambdaPi terms, my brain just goes, that's it. I can't read them. I don't know if anyone can. Maybe Anya can, but I can't read LambdaPi terms in my head. It hurts me too much. And that's all available. So here, look, there we go. And your proof was verified, Stefan. Hallelujah. And on the other hand, if you want to, we can use the LP version, which does it, the whole thing, but generating LambdaPi terms. And the LambdaPi terms will get checked by Deducti. I'll come back to that if you want to see the output. So when did I start? At about 10 past, so I've got 5 minutes. So here's, don't you love, that's a matter of trust. I love that picture. If you've ever been to Thailand, you can go to the show and see them. What have I got? What have we done? Sort of, we got, to me, it was useful to clarify this process over here, to make sure I understood what I was doing, why I was doing it, and when I was doing it. Oh, damn it, wrong one. And we got the GDV LP implemented. That's taken a couple of weeks and summers in France, and I'm happy with it. What are we working on at the moment is we have a proof format for causal connection tableau that came out in the Weidenbach 60 workshop just recently, and we'll write up the full version, and we can verify these tableaux in GDV. I'm working with Alex Steen and his students and 2 of my group on verifying Tarskian models and crypt key models. Particularly verifying crypt key models is interesting because you have to put yourself into the modal context, and then that gets translated to first higher order logic and things go there. So we're working on that. Something interesting coming up, and I mentioned it, is the proof verifier competition. The idea is we're going to take, say, 100, well, not we, I'm out because I'm entering, but they're going to take 100 proofs, which are good proofs, and then 50 of them they're going to break in horribly subtle ways or obvious ways, then hand them over to the verifiers, and the verifiers have to give thumbs up, thumbs down, or give up, I can't tell. And then we see how which proof verifiers can most correctly detect bad proofs and good proofs. So here we're saying, yeah, so we're working on some symbolic, I've mentioned that. Scholarmization, we're working on that with Martin Reiner from TU Wien. And I want to talk, I'm thinking a little bit about modalities, because when we talk about in this empirical process, this evidence, computers tend to think, you think in probabilities, but people often think in modalities. So people say, it's likely that that tool gives the correct answer. Most of the time, what do these modalities mean? So I'm trying to think is, can I build up some sort of modal structure that applies to proofs and models? So that's the main thing. And I can answer questions, or I'd really like to talk a little bit about what happened at CAST, because I only got the data out last night. So what would you like me to do, Matthias?
You have time, so I would be interested in what happened at Cask.
Okay.
I'd like to see the LambdaPi code that you output for your proofs.
The LambdaPi code. Let's see, that just finished.
It might hurt your brain, but you can look away.
I'd have to run something and save it. At the moment this run, it deleted everything at the end.
Oh, great.
Yeah. If you email me, I will do a run and store all the files, and I can send you a zip of it, no problem.
Cool, thanks.
Yeah, sorry, I can't get it immediately. It's a little bit in the middle of the framework, and the framework cleans up when it says verified, clean everything away. It might be an artifact of Xenon Modulo's LambdaPi code terms. Anything else about this material? Then I'd quickly take 5 minutes to talk about Cask. So here are the proofs from Cask, and we've got them all. Everything's all there available. And I'm going to find one proof. Let me find this one here. And I want to find the iProver. Which one is that? CVC5, Vampire. No, that's not the one I want. No, let me, sorry, I have to find a nice one to illustrate this. There it is. And I want it from Drody, this guy. So here's the proof by Drody. This is the system out of Oscar Contreras. And the proof, as you can see, it's got the timestamps on the front. And down the bottom, you can see these proofs get into horribly big things because he does avatar. And there's the last proof step. And this is the list of the parents. All right. And in that proof step, there are 1,219 parents. All right. So then I went out and I extracted that proof step and ran it again. And it turned out that only 663 of those parents were actually needed for the proof step, because he just, well, this guy, Oscar, tries to minimize the list, but he says he's just used some hacky algorithm. So he doesn't extract exactly what was needed. It was done by a SAT solver, as you can see there, like that. And let's look for another one. So I don't want to say that. So I found the extreme examples. I got one from Leo 3 that had 950 parents and only needed 14 of them to actually do the inference. So what's happening is that these guys will drink your beer and eat your sausage. You've got to be careful. They take the entire list of everything they sent down to the SMT or the SAT or the ATP. In the case of Leo, he sends it to E. And then they just report that entire list as the parents rather than trying to find the unsat core. And this is not good. So one of the things I plan for the competition next year is to somehow put some pressure on removing redundancy on the parent list. Now, of course, how do you do that? This is hard. And I don't even know how to check if it's been done correctly, but it's kind of an idea in my head that came out of this observation. The other thing that needs to be done is here, you know, let's take a Leo proof. Where's Leo's proof of this one over here? Leo. There he is. Here's Leo's proof of some higher order thing. We go to the end of the proof. And there's it. There it is, the parents. There's the parent list coming out of Leo. And what is the inference rule? The inference rule is called E, because it's a call to E proof. It's E. All right. Now, then we got to even ask ourselves, is calling an external system really an inference step? Because inside E, there's a whole lot of inference steps. E did some work. And in fact, I analyzed this one, yeah. And so E used only 14 of these to get a nice little proof, something compact. And so an optimal thing or a very good thing to do would be to take the proof of these subsystems and graft it, you know, expand it, expose it, and graphed it into the bottom of the proof that called the subsystem. And I spoke to Alex Dean on Friday. He said he found some time, and he's working on that in Leo, by the way, Stefan. He's found out how to extract your proof and graft it on into his proofs rather than just say inference by E. So that's good progress over there. But generally, there's a general question is, what is the granularity? What is an acceptable proof? Is calling E an acceptable? Let's say he really optimized it. So the parent list only had 14. And he just said, inference step, the inference rule is called E. Is that acceptable? Or does it have to be exposed at the finer granularity? I don't know what the answer is to that. And next year's TP-TPT party is going to focus on this. What is an acceptable proof and how one can be produced and issues related with that?
I mean, the real question is, can E say in one step, I just called E?
Well, I do know, I think this is correct. And Stefan told me from...
Memory variable.
Yeah. E can't verify all of its own inference steps. Correct, Stefan?
Yes.
Yeah. And that's because when you put an inference step as a problem, then the strategy gets changed. And so you get something different. E does something different. And it can't do its own step. I mean, and so these matter. So if you have a proof artifact, if you use a proof in a planning system, you know, you've converted some PDDL to logic and you do a proof. The proof is the sequence of steps. And therefore, it matters to have a properly formatted proof for it to be useful. I see people hovering around a desk.
Something wants to turn
The
off.
TV's
in 5
about to turn
seconds.
off. But I suppose we can see you on the TV at the back. Right? But
No, really don't. No, I was hoping it was just the computer. But...
so now these have gone green.
Yeah,
Maybe if we
But did
Oh,
the
display
recording
on?
stop maybe?
displays on.
Yeah,
No, the
that's the
recording.
center.
Is it?
Yeah, because it's
Okay,
okay,
I
that over
can see
there.
it. Yeah.
Yeah, well,
It's coming up on the big screen.
yeah.
Yeah. Well, actually, that's sort of the end of my story, and I've run over my time anyway, so let me stop there. If anybody would like to talk about this, email me. I'm looking for input and suggestions and ideas of how I can clearly define in an unambiguous way what is an acceptable proof in what contexts.
Okay, thank you very much.
Very good.
Let me start with a quick question. Will there be a full verification, so a full workflow track at the TPTP next year? So one where you take, instead of just the runtime of the solver and the checker.
No, there won't be. And I'll tell you why. It's for a very pragmatic reason. The proofs that are coming out of automated theorem provers, I thought this year I could get them structurally correct, but my observations are, I think we need another year for the developers to get their proofs to be structurally correct. So I'll do structural testing again next year, and possibly also testing that the leaves follow from the problem. But I'm not going to do the full verification. I think it just won't work because the guys need another year to get their proof formats correct. So looking for in 2027 for that.
Interesting.
Yeah.
Yes.
I have a reaction there. So you gave a very nice example there with the inference E. This is Muskwakis memory location, and you put there the inference.
Sorry, I can't hear everything. The sound's breaking up a bit.
Yeah, it was just a comment, I think.
Yeah, it's just a comment,
Just
no
a comment.
question. Yes,
Yeah.
there's no question, just a comment.
Oh, okay.
I see it immediately.
Yeah. Yeah, I think there's a real thing. I know Stefan might be able to comment because Stefan, you call, is it minisat? No, what's your sat solver? Picosat. Yeah, and when you get something out of Picosat, do you try and extract the unsat core in the inference?
Yes.
You do?
Yeah.
And you get that information back from Picosat?
Yeah.
Okay, so that's what I think everybody needs to be doing and it's clearly not the case at the moment, but yay for E.
I think.
The question, if if PicoSat reports it, that's great. But if you call an SMT solver, I mean, what does an SMT solver say? Sat? Unsat? I mean, you can get more information out, I know, but extracting it is not just on a practical basis of getting the work done, I think is going to be, that's a year of work in there.
The format to get the unsat core is pretty easy. So it's just unsat core, I think, and the name of the premises. So that's pretty easy.
Is that for SMT?
Yes, for SMT, it's pretty easy to get.
Right. And it's easy to get for ATP. And obviously for some SAT solvers, I think SAT, you can get it. So it's technically possible. And so now it's up to the developers of Leo and Vampire and Drody and all the other guys to do the work to, when they call an external system or some subsystem, to extract the unsat core and do it. But it might not always be that. I've seen some inferences where it's not where it gets to false. They just do an inference that leads to another formula, not to false. And again, you need to get the list of which formulae were used to do that derivation. Again, I think this is not impossible. It's just technical work that will take some time.
So Geoff, that's what the developers need to do to reduce redundancy in their proofs.
Right.
But do you have any tools for detecting redundancies? You were saying before you sort of did it by hand, but is this something you could do in advance so that you can accost the developers and say, look, see, you're doing this bad thing?
Yeah, sure. What I can do is, like that example I showed you, is I extract the inference step and then set it as I have done as a verification problem, and then run it another theorem prover that tells me which of the parents it used to do that step.
Mm-hmm.
Now, you've got to be a little careful there because the other solver might use a different set of parents than the original one.
Yeah.
So I don't have a precise way, but I can certainly detect cases automatically. I have to write some software for that, of course.
Cool.
All right, good. Thank you very much, everybody.
Yeah, thank you. Okay, so yes. Last point of I'm looking for inspiration for what I'm supposed to talk about next week in the WG meeting. We have to present how much great work we did.
Do we start?